So, hi everybody. We're going to present you this tutorial on out-of-tree passes, which is how to live out of tree in LLVM and still do your transformation the way you want. But first, that's a tutorial. So I expect you from asking questions during the session and not only at the end. So if at some times something seems wrong or doubtful, just raise your hand, ask your question, and it will be easier for everyone rather than wait at the end of the 1 hour tutorial and it will just lose the context. So both of us are working for Quarkslab, which is a French society specialized in security. Nothing to do with LLVM. It does because we are writing an obfuscating compiler, so to obfuscate LLVM representation. And when we began, we had to choose between out-of-tree development or in-tree development. And as a start, we chose out-of-tree, and that's this kind of lessons we're going to share with you today. So first, anyone that wants to follow the tutorial based on the actual source code can just go on GitHub and get the source. Actually, all the code samples that will be displayed during the tutorial are literally extracted from the original source, which means it's a kind of literate programming talk. The good side effect is that everything I show you just works. The bad side effect is that the formatting of the source code sometimes has to match with how I want to display it. So the formatting is not perfect on the source code. It's not that I am lazy or I'm not applying what I'm telling you to do in the tutorial. It's just that I was a bit lazy to go further than this. So let's begin. I assume this is an introductory talk. So if you're already familiar with LLVM, like an expert LLVM developer, most of the part here will be redundant with your knowledge. But better safe than sorry, I introduce what is all the principle. So at the top level, you got an LLVM module. Inside the module, you have several functions and global variables, type declarations. Each function has a control flow graph in terms of basic blocks. And each basic block has a list of instructions terminated with a terminator. All the instructions are in SSA form, single static assignment. And so if you want to take either one value or the other, you have these phi nodes. So if you come from the true branch here, A will have the value A prime. And if you come from the false basic blocks, then A will have the value A second, right? Nothing new there. And the last thing you need to know to follow the tutorial is what is a pass. A pass is a basic block of the compiler which turns a module into a new module, which means you get a bytecode. You apply your pass, you get a new, updated or not, bytecode. OK, everybody already knew this, but just to prepare everything. Well, the tutorial is organized like a game. So you have the first game setup, and then you have different stages, and then you have the final boss. And that's the story we're going to tell you. So first, we are based on the latest release of LLVM. So you just need to compile LLVM once, install it somewhere with clang, and then you will never touch this source again, because you're working out of tree, which means you don't modify the LLVM source code. You're going to add extra modules, but you don't modify the code. So you install LLVM once, and then you play with it out of tree. And that leads me to why doing stuff out of tree. One of the nice points is that you never get to mess with the LLVM source code directly. You don't recompile LLVM each time you do a modification on your pass. If you want to deliver your pass, you only deliver your code, and you assume that your customers or your users already have an LLVM version deployed, which match the LLVM version you're using. And that's easier to begin with. So LLVM is loaded, and then you select the difficulty of the tutorial. So this is an easy tutorial, okay? No hardcore stuff here, just the basics. And then you do the stage selection. We're not going to speak about how to develop a front end or how to develop a back end, nothing about in-tree, whatever. It's out-of-tree path development. And then the OS selection. You can see that you can't select Windows. That's not some philosophical stuff from me. It's just that out-of-tree path development is not supported on LLVM. If you try to do this now through cmake, you will be just rejected, like it's not supported. So it's not supported by the tutorial. It's not supported by LLVM. It has to do with dynamic loadings. It just doesn't work. So it's for Linux and OS X. And then it's up to Adrien to talk.
Thank you, Serge. So as we said, the first thing we have to do is to create a cmake project. So in order to do this, we're going to use the LLVM cmake support, which is pretty advanced. So we're going to create our project, and we're going to see how we can register our path with OPT, and how we can also register it with clang. So first of all, this is a new project, so we have to organize our files and everything. So the first file to have is obviously the cmake list.txt to declare the cmake project. Then we have some cmake auxiliary files. We're going to see why for Python, and then our first pass, which we call MBA, which means mixed Boolean arithmetic. So it's a kind of technique to mix classical Boolean arithmetic with integer arithmetic, thanks, to create obfuscating computation. So the first thing how do we create our cmake list? So the first thing to do is to add the user to declare where LLVM is installed. So through the LLVM root variable, we will beat a small sanity check to see if it's a real LLVM installation. So that's basically it. So then we use the find package cmake command to find LLVM. So if it doesn't work or it's not a valid installation, it will just fail. And then we use two interesting things. So the add LLVM file, which is provided by LLVM, which declares the function we will use to declare our new path, and the handle LLVM options, which declare some basic LLVM variables like LLVM definitions and LLVM include years. So like when you use cmake, if you have already used cmake, when you use an external library, you always add the definitions and the include years you have to add to your project. So that's basically what we do here. So nothing fancy and nothing new, nothing really new. And two variables you have to set. So the LLVM runtime output integer, LLVM library output integer. So it would tell to the add LLVM function, add LLVM module function, sorry, in which directory it has to output your dynamic library and your binaries if you create some. So once we've done that, so we have injected LLVM into our cmake project. So we can now declare our path, which is the MBA path. So the one, okay. So you have mail, yeah. So the new, yeah. Okay. So just a small demonstration. So just check. Okay, that's fine. So here I'm launching my cmake command. So we detect the compiler and everything. You will find LLVM, and that's it. And if I compile my project, I can see that there are three. You see the mouse? No. Okay, cool. You can see that there are three .so files, so three shared libraries, one for each path. So we're gonna explain the MBA one, and Serge, which we talked about you for the reachable integer values and duplicate BasicBlock. Anyway, so here we've just compiled our three bases. So yeah, just to finish the cmake list, so we have the add LLVM loadable module line, so which declare the shared library we just seen. And so as I said, there is one path per one shared library, sorry, per path, which we can use through OPG and which we can use through clang. So we just got, sorry, we'll see that later. So for instance, here I can use clang to compile, sorry, it's not the, here we are. So here I use clang. I said to load my shell libraries and to compile a simple C file. So the C file was just this one. So it's just an addition of 2 integers. As we can see, the output of the LLVM bytecode is modified. So it's not just an addition. We see what it is afterwards. So how do we write a small and basic pass? So it's just nothing new if you have already written a pass, an LLVM pass. So it's here we're working on a basic block. So we just have to implement the runOnBasicBlock function and to return true or false whether we modified or not the internal IR. The second thing to do is to register our pass in order to be used by OPG. So for that, we use the register pass template class, and we create a static object within our shell library. So it will be the constructor of the register pass class will be called when we load the shell library. So there are 4 things to define. There is the name of the pass, which is MBA, which is used in the CLI in the end. There's a human readable description, which will be print within when you ask for the help of OPG, for instance. And there are 2 flags. So once we said, are we modifying the control flow graph? And the other one, if we're writing, whether we are writing or not an analysis. So moreover, as we are out of 3, we can't rely on the, the existing test infrastructure of LLVM, and we still want to test what we're writing. So we can still use LIT, which is the LLVM's integrated tester. It's available actually as an external pip module, module. So you can just write, you can just launch pip install lit and you have it. Then you have to write a small lit.conf file which describes which file has to be launched and so on. We won't show this in here, it's not really interesting, but you can have it on the GitHub if you want. And the one thing we do just for convenience is that we're adding a check target in cmake, which makes the developer able to type make check just to launch the test. So basically, it's a custom target which will launch the Python interpreter with lit and the directory with our test, and that's it. The last thing we can do is to make the pass usable from clang. So as we can see, we have registered for OPG before. This won't register the paste for clang, so you still have to do another registering thing. So it's basically the same model. So you have a class register standard passes, which you create a static object, and you have 2 parameters. You've got an extension point. So it's really important to understand this one. It will say, I want to launch my pass before all the optimizations or after all the optimizations or maybe in the middle of them. So you've got, I think, if I remember correctly, 5 or 6 different extension points. They're also different whether you have a module pass or a function pass. So you have to be careful about what you do. And the second parameter is just a callback. And this callback basically adds our pass into the pass manager. All right. If you have questions about this, talk now. Okay. So now that we have set up our cmake project with our pass, so for now it does nothing. We have just a path that does anything. So we're going to see how we can create basic manipulation of the LLVM here, how to write a simple test scale using lit, and afterwards we're going to see how we can do some statistics about what's going on and to add some debug information which can help in the future. So I talked a bit about mixed Boolean arithmetic. So here's an example. You can prove that modulos 2 by the persistent n, so on 32 bits, for instance, a plus b is equivalent to do a XOR b plus 2 by a and b. Okay. This is easy to understand with 1 bit, and you can prove that it works on any number of bits anyway. That's not we're not going to prove that. So, but we use that for call obfuscation a lot.
Yeah.
Yeah.
This is based on the assumption that false maps to 0 and true maps to 1, correct?
No. Actually, this works with any number of bits, not just only with 1 bit. So if I have A and B that are 32 bits, this still works. Okay, I can show it to you why later if you want. But so you can create actually.
What?
I mean,
A and B are originally Booleans, right?
No, they're integers.
Integers.
They're integers number. Yeah, so the plus with the circle is the XOR, and the small cap here is an AND, a logical AND. Yeah. Sorry? No, XOR.
The plus mean plus, and the plus cycle mean
XOR. And the last one is a logical AND.
The purpose of this obfuscation is that it's difficult for a solver to combine two kinds of arithmetic.
But you're assuming for every seed that true maps to 1.
I assume we don't have the concept of true actually. We just have bits with 1 or 0, you know. And yeah, so what's interesting for obfuscation here is that, for instance, LLVM or GCC can simplify that kind of thing for now. But, you can try it. The first time I saw this, I was like, okay, it's easy. Just give it to LLVM, but it doesn't work. Anyway, so what we need to do, so we started with the BasicBlock because we have a BasicBlock pass. So we need to go through all the instructions and to check whether it's an addition. If it's an addition, we need to check whether if it's an integer. If it's that, we need to modify the instruction. So what we do here is that we use, so we go across every instruction using a classical iterator. We do that because we're going to do in-place modification, so later on. So we can't use, for instance, range-based iterator in here. Then to check if it's an addition, so an addition is a binary operator in terms of LLVM class hierarchy. So we check whether it is a binary operator using LLVM's DINCast, which is different from the C++ dynamic cast. So they have their own casting mechanism, which won't use RTTI and everything. So that's why you need to use the DINCast here. If it's a binary operator, then we're going to check whether it is an addition, so just by checking the opcode. And then we're going to check if the type is an integer. So that's basically how you filter every instruction step by step in a BasicBlock. Once we've done that, so we've got our binary operation, so bin up, and we need to create our new instruction. So in order to do that, we're going to use the IRBuilder class. So it's a wrapper around every other instruction that exists in LLVM. So here we create an object builder, which we insert operation before our bin up that we found. So here we create the addition, then the door between the two operands, then the multiplication by 2, and the n between the two operands. So that's basically the formula that is in this slide. So once we've done that, we need to replace every usage of our old addition by the new instruction that we created. So for that, there is an LLVM helper which is called replace int with value. So it basically does 3 things. The first one is to actually replace, so it will call the function replace all usage of value, something like that, anyway. So it replaces every usage of our addition with our new value. Then it will propagate debug information. And the third one is that it will delete our old instruction from the BasicBlock. That's why in this function we're going to, as argument, we have the IIT, which is the iterator we had here. So it will update this iterator to be valid again, so we can remove the instruction in place and not, for instance, store every instruction we have to remove and remove that afterwards, something like that. So that's really an interesting function, and it's pretty convenient here. Okay, so now we're going to see how we can write a simple test. So we will use lit, as we said. So basically, lit, if you want to write tests with lit, you're going to write one source file per test case. The command you need to run to do your tests are written in commands. And you have a small macro processing system which you can use to give as input some configuration. Like, I don't know, where is LLVM, what is the suffix of my library, something like that. And you can combine this with a tool which is given by LLVM, which is called file check, which is kind of a better grep. It's really interesting. It allows you to write tests like this. So for instance, here we have a small test which will compile our C file here with clang, apply with opt the MBA pass, and then run file check. So what does we tell to file check? We say at this line, you have to compare with inside the generated bytecode whether we have an AND operation instead of not instead, but if an AND operation is present here, so the AND operation we saw it before is inside the MBA expression. So we ask, actually what we ask to file check is whether this has been transformed or not by our transformation. So we can do more advanced stuff with file check. So there is a prefix operation. So here we run two things. So we run our pass with a ratio of 1 and then a ratio of 0. The ratio is an option Serge will present afterwards. It basically says, okay, you have to replace every addition you find, or you never replace any addition. So ratio equals 0, basically deactivate the pass. So what we ask here is when the pass is activated, so when the ratio is at 100%, you need to filter the check which are prefixed by checked on. So as before, here we check that we have a multiplication instead of the addition here. And on the other side, if it's deactivated, it will only filter with the check off. So we'll check that the multiplication is not present in this case. So for instance, if I run make check on my pass. Oh, sorry. This is live fixing. Right. So here I run the make check. So we saw before make check, we basically launch lit, and we see that every test pass. So the tests are this one. So that's it for the test and how do you develop pass and how you can modify the LLVM here in place and so on. So now there are some bonus things you can do while you're developing your pass that are really interesting. So the first one is how you can collect statistics about what's going on. So here, for instance, we want to know how many additions we modified. So what we do is we use the statistic macro, which defines a variable, a global variable in your CPP file, and the description. And then what you just need to do is to increment this variable, and then you use opt to get the statistics, or within clang. So for instance, here, if I use clang, Sorry. Ouais, comme c'est que j'ai viré là. Sorry, I need to. So if I write just a small function with just an addition, sorry, so it's basic, and then I add the statistics. So here I added the minus stats option to clang. So we will print, and I also asked the minus O2, so the basic, the optimization that we all know about. And here I can see that I've got one MBS, so I had one substitution of an addition within my when I compiled. Another thing you can do is to debug a pass. So you can add debug trace within your pass. So two things to do here. You need to declare a guard or a prefix before including debug.hash anyway. So and then use the debug macro, so which will be activated or which will print the statement inside when you're in debug mode, and when you will release mode, it will simply delete it. So that's convenient if you still want performance and not debug stuff inside your pass. And then you just use the minus debug flag within opt or clang to print them. If you do that, you have the debug information of every optimization pass, so it's not really readable, and so you can filter it with debug only. I'm doing this live. Yep. And for instance, here we just see the first line we can see here is we print the instruction we changed. So that's basically the line we wrote here. So that's all for the stage 2. So now I'll let Serge present how we can write an analysis in a LLVM, how we can use it.
Before, do you have any question on that part? Yeah. Or that's OK for everyone? Yeah? The question is, we have to repeat the question. The question is, how do you control when the pass is applied relative to other passes?
So that's the session point we saw before. So if you're using OPT, it will take the order of the arguments you give. All right. So if, for instance, if you say OPT minus O2 minus MBA, it will first run the optimization and then your pass. If you revert these arguments, it first run MBA and then O2. Within Clang, that's why they're using the extension point. So here, when we register, we have EP early as possible. So this tells when the pass manager will insert. There is a pass manager populator, and then it will insert first the class we declare, then insert the pass for the optimization, and that's it. And if you change the extension point, it will insert them at different points. So the points are statically built in the LLVM. As I said, there are 5 or 6 of them. So that's how you can control it.
Basically, opt gives you a better control over the pass ordering because it does what you're telling him to do. For example, if you want to apply the MBA transformation twice, you can do it with opt by calling minus MBA twice. But in Clang, you can no longer do this. Yep. You just register your pass at a certain extension point. And if you want to apply it twice, you have to register it twice at this extension point.
And also, there are some drawbacks with this. For instance, if you have a module, you need to be careful because this extension point won't work because you only work with function pass and some stuff like that. That's not really documented. You need to read the code to understand this. So there are some drawbacks here. For instance, here, if you don't use optimizations, it won't be aided because you need to use the extension point that says even if there is no optimization. So that's something that are not really documented, so you need to read the code to really get it.
The Clang extension is not meant to be used out of tree. It's my guess. It's not documented a lot. But still, if you want to integrate your out-of-tree pass into Clang, that's the way to do it. But it's not advertised as a good way to add extension point from an out-of-tree pass. Just a slide way we found. So now let's go to an analyze. How to write an analyze out of tree. So what we will learn in that part is how to depend on existing analyze, and how to write a function pass, and what's the difference between analyze and a transform, and how to describe the dependencies between your pass and other analyze. And as a bonus, we will talk a bit about LLVM coding rules, how to follow or not to follow them. Let's roll. The analyze we will describe here is a really simple one, because that's a tutorial. But it's still useful, always in the context of obfuscation. The problem in obfuscation is sometimes you need to pick random values from the context where you're doing your stuff. And these random values still have to be valid in terms of SSA form. And so to do this, we have this analyze that just binds every basic block of your function to a set of variables that can be used by this basic block. For instance, when you begin your function, the only local variable you can use is the argument of the function. And when you go on, you keep creating new values, and these new values will be added to the reachable integer values. So I just described the algorithm here. To begin with, we have this entry point there, and let's assume there is no argument to the function. So there is no visible values, but we define a new value. And then we will walk the dominator tree and get the successor of this block. There's one successor in the dominator tree, which is this block. And so the visible values of this block will be all the visible values of the previous block union the defined values, which is here only v0, and it defines its own new values. Because we are in dominator relationships, you don't use this loop, and you get the successor here. And the visible values of this basic blocks will be all the values from this block, and it defines a few new ones. So what we are going to do is walk the function, walk the dominator tree, and keep in filling the defined and visible values, and then build this mapping between basic blocks and visible values, and make it available for other passes. Basically, an analyze is just a pass. So it's like a transformation. You have to register it to make it available. You have to declare it in cmake. So when you declare it in cmake, it's just a regular loadable module, nothing different from a transformation. And when you register it for opt use, you do it the same way, but the last argument is set to true because it's an analyze. And as a side effect, an analyze doesn't modify the internal representation, so the previous flag here is always set to true too. But an analyze is quite different from a transformation because it produces something that will be consumed by another transformation. And if you're using in-tree analysis, everything is available. When you're out of tree, some analyze come from the tree, and some analyze come from your code. So you need to export the class declaration. If you may have noticed that when you defined your transformation, you only wrote a CPP file, no header, because everything is registered through static constructors. You don't need to export anything. Here, you will need to export your class declarations, maybe the structure you're producing to hold the result of your analyze, so everything goes into a header. So you have to write this. And then opt will need to know the code from your analyze. I mean, you are using an analyze in your transformation. It's OK to declare the dependency to include the header. But if opt doesn't have access to the code, it will break. And then an analyze in LLVM is built as a function with an internal state, and the internal state holds the result of the analyze. So you have to take care of this, which means that part of the API of the analyze, which is described here, is first, all you declare the dependencies to other analyzes, get analysis usage. The typical runOnFunction you have to override, and a specific getter to get the result of the analysis. So I will go through this. But before, just understand how the legacy pass manager works. So basically, when it meets, so it will process your transformation. And for each transformation, it will get the dependencies through the get analysis usage method, and work through all the analyses, run them, and so build all the internal states. And then it will run the entry point of the pass. And from this entry point, you can use the get analysis method to get the instance of the analyze that has been filled by the pass manager. And from this instance, you will use the getter to get the actual object that holds the result. So first, declare the dependence. As I show you, the dependence, our pass depends on dominator trees. Dominator trees come from in-tree. So we just have to fill this analysis usage object with, we require the dominator tree pass here. It has to be run. And as it's an analyze, we don't modify anything. So it preserves all the result of previous analysis. So that's for the dependency declaration. And then the analysis entry point. So I'm not going to dive into how we implemented the stuff. If you're interested in it, you can read the codes on the Git and maybe ask questions afterwards, but that's not the purpose of the tutorial. First, I said there is this internal state. When you create a new pass or a new analysis, the pass manager will register a binding between an ID. Maybe you noticed in the constructor there is this ID stuff when you create a pass, and one instance of your analyze. And this is this one instance that will be used during all your compilation. So you have to clear the previous state of your analyze. Then you do your initialization stuff. And at some point, you will want to walk the dominator tree. And to do this, you use the getAnalysis method. So with this, you're guaranteed to get an up-to-date version of this analyze for this function. And then you can use all the getters. So here we are walking through the dominator tree, so we get the root node, and we'll iterate over the successors. We get it here. Then we do the actual smart stuff, but it's not interesting here. And it's an analyze. So an analyze doesn't modify the code, so it always returns false.
Yeah.
You need to clear the result here because you always have the same instance through all your functions. So if I am analyzing first function foo, at the end I will have filled my mapping, and then when I go to function bar, this mapping will be still filled. And so if I keep infilling it, I will have wrong values because I will have references to my previous functions. So in that case, as each basic blocks are uniquely identified by the address I get, it will not cause an issue, but it will make your map grow beyond what you need. So it's really the idea that you have the path manager has a binding between a type through a static variable of this type and one instance of the path, and this is this one instance that is all used for all the function in your module. And if you call your analysis repetitively, it's always the same instance that is used. So that's why you need to maintain the internal state. That's exactly what is done for the dominator tree analysis. I just had a look to the code before writing the tutorial, and they are cleaning the dominator tree when running it on a new function. Any other question? Oh, so I go on. So there is a little bonus here about the coding standard. I don't want to start any religious war or whatever. The nice thing when you live out of tree is that you don't get the processus review of checking in the LLVM stuff, so you just do what you want, okay? Which doesn't mean that you can do bad stuff, okay? But if you have your own coding rules, you can use them, even if they are not the one from the LLVM community. But it's always good to have a common reference. So if you start a new project, just using the existing well-documented coding standards from LLVM, it just put an end to any discussion and you can focus on actual stuff. And it also provides visual consistency with all the LLVM API call you're going to do throughout your code. So I guess it's a good start to just use these coding rules for your project. If you're lazy, Clang format can do part of the formatting stuff for you. For example, use this sync command, so you can add this kind of stuff in your GitHub hook or just do what you want. And, well, it's recommended to read the coding rules. Now, last step of the tutorial, we have seen how to write a path, how to write an analyze. So now we will write a slightly more complex path and just see a few more stuff concerning tests. So we will play with basic blocks, phi nodes, and we will see how to declare this MBA minus ratio option I told you about. And we will also go a bit deeper in the testing stuff using fuzzing. If you followed, there was a talk concerning fuzzing this morning, and I advise you to use fuzzing during your compilation, during your development process. So you have to, you're interested in fuzzing your passes, and how to add a support library, which means how do you link to third-party libraries that just indicate all the stuff you will use for all your out-of-tree passes. So once again, an obfuscation pass. This one is also very famous in the field, duplicating basic blocks. The idea is that each time you meet a basic block, you will duplicate it and guard it by any condition. You don't care the value of the condition because you're using clones. And it just adds some mental charge to the reverser because even by tracing his application, he will see both blocks used. So if blocks evolve in different way thanks to other obfuscation, they will not look the same, even if they do the same stuff. And so they have to reverse twice the amount of code. So to do this, we will, if you want to duplicate the BB0 basic block, you will first create a header with the condition you've been forging. And then you will branch either to the true or false branch, but both hold a clone of the original basic block. And then to maintain the SSA form, because each part we have created different values, you have to merge all the values into one, and then you will use phi-nodes to do this. When you do this kind of transformation, you will meet a few problems. Some are very basic. For example, as your transformation, while iterating over the basic blocks, is creating new basic blocks. If you don't take care, the new basic blocks are added at the end of the basic block list, and so you will keep processing everything and creating clones all over again, so you just have to take care of this. But more interesting is the fact that cloning an instruction does create a new value, because all values are unique, but it doesn't change the operands of your instruction. And while you're creating different blocks, you want the operands of your new function, of your new instruction to be in the same basic blocks. So you have to take care of some kind of remapping there. And so let's go for this. So first, you have to forge this random branching. And here, all the pieces of the puzzle come together because we are going to use the analyze we've just been developing. So we declare a dependency on a reachable integer value pass in our dependency method. And to do this, we need to include a header. So that's why you need to write a header for your analyze, and you don't need it for transformation. And then you use the famous getter to get the actual mapping, right? And then once you have this mapping, for each basic block, you will get the set of values that are reachable from this basic block. And you can just pick a random value in this set, like I do here. And then to build the random condition, this is not the actual code you would write, because this one is pretty straightforward, but you can use IRBuilder, we've already seen, and use the factory create is null that just tests the value compared to 0, whatever the type of the actual value, and it creates I1, a Boolean value that can be filled to a branching condition. So just something here. I've declared dependencies to reachable integer values map. But how does it plays with opt? If I just call opt like this, which is what I intuitively want to do, I mean, just load my pass and apply my pass on my test case, it actually just fails. And the failure is, whoa, error opening there. There is an undefined symbol, and if you have an integrated demangler in your eyes, you see that the analysis is not available. It's because it's defined in another module. So even if the dependency analysis is automatic, you still have to make the code available. So you need to load the actual So you need to load the analysis. You don't need to call it, because it will be automatically called by the pass manager, but the code has to be here. And then it just works. So you can see that this code is very similar to this one, apart from the values that are different, because we are in SSA form. We have this branching here. And the branching depends on this comparison, which is a create is null call. And G is just one valid variable from the context. It could have been another one. It depends on the random generators code. So just to say that depending on analysis, also required to load it in OPT. When you're cloning an instruction, you can use the clone method from the instruction class. But this creates two different values. So to do the remapping, which means to make sure that the instruction from the true branch only refers to external values or values from this very basic block, you need to perform some substitution. So you maintain a map, and you use this very useful remap instruction function, and it will just update the operands based on the mapping available here. And this, the last parameter, means if the mapping is not, if a value is found and not in the mapping, which means that it comes from the outer scope, just ignore it and go on, which is what we wanted to do. And then we need to do the merging stuff. So to do this, we know we want to use phi nodes, but we will want to replace the phi node instead of the original instruction. So we will not use the builder. We will manually create the new instruction. And to do so, there is for almost all instruction a factory called create. And this gets you a newly allocated value. So here we just get the type from one of the clone and say that the phi instruction has two predecessors. And we add the incoming age manually. And if we only do this, the instruction will be inserted nowhere, and we will leak memory, right? So the right thing to do there is to use replace instruction with instruction just to bind this new instruction in our flow. And once it's bound to an existing basic block, then the memory is managed by LLVM, and you don't need to take care about it. Most of the time, you don't need to do this manually. You just use the builder, but it's still possible. And with this, we've done our transformation. And then we want to test it, because one simple test case, as Adrien showed you, is not enough. How does it behave with strange integer size or anything? So you can just use existing open source code and compile them with your obfuscation and check that the validation suite is still working. But there is this TestSmith project that has been developed some 5 or 6 years ago, which is very great because it's a factory for strange C code. And especially when you do obfuscation, but I guess it's valid for regular optimization too, it's very valuable to just create random inputs and make sure everything works the way it should. So it's really well packaged. You just get it, make it, and once you do this, you can write a configuration file which describes all the flags you want to test. So here I have the reference, which is just the regular clang call, and then I had my call to my obfuscation, and bundled with TestSmith, there is a test driver, compiler tests, and this driver will run here 1,000 times both compilers and checks that the output is the same. And by doing so, internally at Quarkslab, we have been detecting a lot of issues. So it stresses your compiler a lot. And when you're not in tree, you don't have all the test case from LLVM, you can just have a pretty decent test suite just running this for every night or in continuous integration. It's just because during my tests, you can even say as long as you don't find anything, or it's just to have it run in a decent amount of time. Sorry, speak a bit louder. Oh, no, here it's just a practical choice, nothing more than this. And then let's speak about the minus ratio option we've been adding to our passes. When you duplicate basic blocks, when you add extra obfuscation stuff, you don't want to obfuscate everything. There's a two main reasons for this. One will be described in a lightning talk tomorrow, so I don't spoil it now. But the other one is that if the same pattern appears every time, for example, the MBA substitution, the reverser will just notice each time it's an add. I know this because it's used as a loop index, and so generally loop index, it's a plus. So here it's a plus, and so everywhere it's a plus, and you're done with your obfuscation. You have to be stealthy when you obfuscate code. And so you want to control, let's say, obfuscate only one add over 100. And to do this, you can add this parametric stuff. So to do this, you can just use LLVM CL framework, which make it possible to declare new options. So an option is just declared by the name of the option, a description, a meta variable, a default value, and whether it's mandatory or optional. But here we also want to add some checks because a ratio is something between 0 and 1. And if we just use a floating number, we will have to add extra checks, but at the wrong place, maybe in our pass. And so we will duplicate it for each pass that uses the ratio. So what we want to do is to customize the parser for the ratio type, which is just a wrapper around the double. And to do this, because it will be used in different passes, we need a support library. A support library is just a regular archive. And so you develop it like a regular cmake library. There is nothing new here, and I'm not going to spend any time on it. In this library, you will specialize the LLVM CL parser for your ratio type. And obviously, you will also declare the ratio class in your support library so that it can be included in all your obfuscations. And the only interaction it has with your passes, and unlike in tree passes where everything is available within LLVM, you have to add this extra link, but it's a regular cmake link, and there is nothing fancy here. It works as it should. So before we meet the final boss, do you have any question on this part of the tutorial, or everything is crystal clear? Crystal clear. So my guess is that you're going to use out-of-tree passes, for example, when you begin your PhD, because you don't want to mess with all the LLVM stuff. You just want to focus for 3 years on your own pass, and you want to interact as less as possible with all the technical engineering stuff. So you will fight the compiler difficulty that is embodied by this red dragon. And if we are lucky, with all what you learned today, you will just use your special move and get rid of this difficulty and go on with your actual PhD stuff. So we are quite in time for this tutorial. So in addition to thanking ourselves, we'd like to thank Mehdi Amini, which did a very in-depth review of the actual code. It's very painful, but we really like him for this. Thanks also to the Quarkslab team, which reviewed the tutorial parts. And if you have any question, you just have 3 or 2 minutes to ask them. Oh, that's okay. Feel free to have a look to the source code on GitHub. There is much more information on technical aspects, just written in the code with comments pointing to the website where the documentation is. So it's meant to be a starter to write passes. Yes, a question. Just speak a bit louder. Just speak louder because I can't hear you.
Can we do at a higher level how we do the duplicate BasicBlock pass? That's it? Comment à un niveau plus, enfin, comment marche la passe bien au niveau?
At the high level, I mean, maybe if I show you the code, it will be clearer for you.
It's not a high level.
That's not very high level, but sometimes for our developers, it's the way it works. So it runs on a function, and then for each basic block of the function, you just don't want to mess with exceptions because exceptions are tricky, so just skip this. Then you check this ratio stuff. I mean, do you want to apply the transformation on this basic block or not, depending on a dice roll? Then here you have the result of your analyze. You get all the reachable values. So this is a set. This is a set of reachable values for this basic block. Just count them, and if you don't have any context to build your random predicate, so you just skip. Otherwise, you just pick a random value here. So you get an iterator here. You advance it because you don't have random access iterator on a set. What am I doing here? So this is where I will store the binding and a baby to duplicate the context variable. So I just store a binding. I don't remember why here. You update the statistic of number of duplicated basic blocks. Otherwise, you have no context, so you do nothing. So once, well, okay, now I remember. Once you've built this, you have this binding between each basic block and a condition. So you can run the actual duplication, which is here. So for each mapping between basic block and value, duplicate the basic block. I'm running out of time. So I get the entry point of the basic block here, just after the fee. I create my condition here. Hey, I also documented the code. Okay, so the code itself is documented right in the, like in the tutorial. Then I split the original block in two, so before the condition and after the condition. And I create two basic blocks, which are available through the terminator instruction here. And then I have to the remapping stuff here. And for each new instruction, I will just check if I am not in the last instruction, clone them, remap them, as I explained in the tutorial, insert the clone instruction in each of the basic block, because cloning doesn't insert the instruction anywhere, remap them for both parts, create the fee nodes, record it as a remapping, replace the instruction from the tail, from the original tail, and I'm done. So that's not very high level, but that's some kind of explanation of how it works. And that's okay. Thank you very much.